Good morning, everyone. Good morning, everyone. So today we're going to discuss about stability analysis. So you might wonder why are we going to study about stability analysis, whereas we have already seen the stability criteria in first order and second order system, right? So in first order and second order system, let's refresh a bit. For first order and second order system, it's pretty direct. It's straight to the point when you want to study the stability of the system. We have basically for first order, we have to look at the position of the poles. If on S plane, so we have sigma and j omega. If the pole's position situated on the left, then we will have a stable system. But if it is on the right, this is when we have unstable system. Why? Because sigma represents what we call decay. If the decay is positive, it means exponential. Decay means exponential response. If the exponential response is positive, it means on this side you have a keep on growing response. But if you have a negative decay, it means you have your decay that goes towards a certain finite value and not to infinity. So for first order is straightforward. And the same case is also applied for second order. We can use position of the poles. So for position of the poles, if you have both of your poles on the left hand side, you will have the system stable. If it is on the right hand side, then it will be unstable. But you also have another choice, not by looking at the position of the poles, but you can also look at the what we call damping ratio, right? If we have a damping ratio, for example, there are 4 cases of damping ratio, so I'll let you revise a bit. So there are 3 cases of stable damping ratio, right? Where we have over damped, critically damped, or under damped. Whereas we only have undamped criteria where it is not stable, yet it is also not unstable. So it is what we call marginally stable, right? So that's for first and second order. So why do we now still discussing about the stability analysis? Well, it's because in real system we won't only have first and second order system. We will have an order larger than 2. So what will happen when you have an order larger than 2? It will be quite difficult to find the poles or roots of the equation. And of course, finding the damping ratio doesn't make sense anymore because it is not a second order type of system. So you need to approximate or do other stuff to determine it. So basically, and then another case is when, for example, if you have a system with feedback. So when you have system with feedback, so imagine you have GS on forward and HS as feedback transfer function. So in this case, your transfer function get more complicated, right? So becomes, right now that if you simplify this, become GS plus 1 plus GS over 1 plus GS HS, and depending on HS and GS, we know that the denominator now will have an order larger than 2, right? So this particular denominator can be pretty complex. So when it is complex, it will be complex to find the position of the poles, and even more, it won't be relevant to find a damping ratio. So what do we do is that we will have another criteria, another mathematical tools that will help us in determining the stability of a system. So here in this chapter, what you will learn is basically you will learn how to determine the stability of a system using mathematical tools, which is called Routh-Hurwitz criteria. So we're using this particular method to determine the stability of a system with an order n larger than 2. It could have any value of n. We will be able to determine the stability of it. So in determining the stability, the Routh-Hurwitz criteria has 2 different cases. The first one is what we call normal cases. We'll see it later. And then the other one is the unusual cases, which we will study in part 2. before we start that, what we're going to do is we're going to revisit the definition of system stability. So stability can be divided into basically three types of stability. So in terms of definition in regards to natural response, so what is natural response? Again, if we plot the time response, there are two parts. There are the steady state part, which we call forced response, and then there is this part, the transient part, which we call as natural response, right? So in terms of definition, there are three types of stability in regards to this transient or natural response. The first one is stable. The first type of stability is stable. When is a system stable? A system is stable when the natural response approaches. So that's something that I want to correct here. When if the natural response approach a finite value, not just zero, a finite value, as time approaches infinity. So what does this mean? It means that if I plot my time response, as time goes towards infinity, my natural response here, it doesn't continuously grow. It will tend towards a finite value. So this is a finite value, right? So it can be a certain value, or it can be in other case. For example, in other case, what we can have is, for example, it can start from a certain value and it goes towards zero. So this is also, and then constant. So this is also a what we call stable. So stable means it has a finite value, right? So that's the first criteria of stability. The second one, so it's the opposite of stable, it is unstable. Unstable is when our natural response approaches infinity as time approaches infinity. So if I draw a graph of time response, as time approach infinity, your response goes towards infinity. It can be plus infinity or it can be minus infinity. So it doesn't have a finite value. It goes towards values that keep on growing or keep on decreasing. So this is what we call unstable. And finally, we have a system that we call marginally stable. So what is marginally stable? A system is marginally stable if the natural response doesn't decay and does not grow. So is that not decay? So for example, in stable, it decays. In unstable, it grows. But here, it doesn't decay and it doesn't grow, but remain constant or oscillate. So for example, a time response that look like this, constantly oscillating, this is what we call marginally stable. So for example, for a second order system, we have seen this type of response, right? So this is what we call undamped system for second order. An undamped system where your pulse position is on j omega axis, where you only have oscillation but does not have decay. So this is what we call marginally stable. So that's the basic definition of stability. You either have stable response, unstable response, or marginally stable response, right? And then there's another definition related to the input and output. So a system is stable if every bounded input yields at bounded output. What does this mean? For a stable system, if your input is bounded, I mean if your input is a specific value between specific value, right? So input, your output will also be limited in between a specific value as well. So if you have an input, for example, imagine if you change or you vary input from a value of 0 to 10, your output will also be limited between a certain value. I don't know, probably minus 10 to 20, but at least a limited input, right? A bounded input will have as consequence a bounded output as well. If you have, for example, a limited or bounded input but an exponentially growing output, then the system is unstable, right? So that's the first definition. And then another one is a system is unstable if any bounded input has a consequence of an unbounded output. So if the system is bounded, input is bounded, but the output keeps on growing, that means we have an unstable system. So now let's go to an example, right? So imagine if you have a system like this. So now look, you see, we have a system that has, what's the order of the system? If we look here, we have 3S. It have been factorized to make it easier for us. So it is the forward only. Yeah? So for the forward transfer function, the system is of a third order system. But remember, our system is not just the forward transfer function, it is the whole thing, the whole system, including the feedback. So how do we find the transfer function, the n transfer function? So if I can write over here, the n transfer function should be a transfer function, an equivalent transfer function, let's say I'll call it as GS, that has the same input of RS and same output of CS. So what you need to do is you need to simplify this transfer function. So how do we simplify it? So we have learned in the first part of the second chapter of analysis of system. So basically the GS is, let's say we call this transfer function as G1S. So here we have a feedback transfer function of HS equals to 1, right? So the transfer function, the complete transfer function GS is G1S over 1 plus G1S HS. So if we write it down, so G1S is this whole bunch. But remember, if you want to study the stability of a system, which part of the transfer function that you're going to be interested in? We are going to be interested only into the denominator of the system, because it is in the denominator that we will find the position of the poles, right? So we're going to be interested only in here. We want to make this equals to 0. So let's try to write this down, equals to 0. So it's 1 plus G1S. So G1S is 3 over S multiplied by S plus 1 multiplied by S plus 2, and then multiplied by HS. So HS luckily is just 1, so multiply by 1. So you see, now we have a transfer function, a denominator. So let's say I call this as numerator of GS. Here it is the denominator of GS. So the denominator is not just, it doesn't only have S plus 1 and S plus 2. If we develop this, it is basically, so S plus 1, S plus 2. So here you have S plus 1, S plus 2, plus 3. So this is the denominator of the transfer function GS that we will make equals to 0 in order to find the poles. So you see, to make this thing 0, to make this whole thing 0, what we need to have is we have to have the upper part of the system equals to 0. So this is luckily it's not that difficult. It's quite easy. But imagine if we have a larger system, it will be much harder than this. So how do we solve this? So if you try to, so this one is quite easy. If you try to solve S multiplied by S plus 1 multiplied by S plus 2 plus 3 equals to 0, you find 3 poles, and the 3 poles are, so you find sigma 1, sigma 2, and sigma 3. You find the 3 poles that's indicated here. So you find one real pole at minus 2.672, and you find 2 complex poles at plus minus J 1.047. So you find 3 poles, and we'll see that all the 3 poles are basically situated on the left part. So they are basically situated on the left part of the S-plane. If they are situated on the left part of the S-plane, what does that mean? It means that the system is stable. And then we can see that, for example, if we use MATLAB to plot the response, we have the system is stable. And then there's another thing that we can see, that the system has basically 2 complex poles. And the complex poles means that we will have an oscillation and ondulation. And in this position, this is basically an overdamped and an underdamped system, right? It is just like a second order system and underdamped system. That's why we have this type of time response. So as time approach infinity, I'm sorry, I have written on the text here, but it says as time approach infinity, the response approach 0. Well, now it's not 0. There's a mistake here. The error approach 0, but what happened here is basically the response approach a finite value, which is now the finite value is 1. So it is a stable system. We have a specific value for input 1 over s, and we have a finite value of output which is equal to 1 after certain ondulation, right? So this system is stable. So this is a revision on stability of system, but now with three roots or 3 poles. So it's bounded input yields in bounded output, system is stable. So we can see that. So this is another thing that we have seen. Stable system have poles only on the left part of the left half of the plane of S plane. So let's take a look at another example. So if just now we have looked into an example of a stable system, now we're going to look at an unstable system, right? An unstable system. So I'll let you do on your own here the demonstration to demonstrate this thing. So we have now the transfer function of 7 over s multiplied by s plus 1 multiplied by s plus 2, and we have a feedback. So the feedback, let's say we call it as hs, it is 1. So you have the overall transfer function of, again, is g1s, if I call this one as g1s, over 1 plus q1s hs, right? So, and then if you develop this part, you'll get a certain value, and then if you try to find the poles, you'll end up with 3 poles. So there's one real poles on the left hand side, but now we have 2 poles on the right hand side of the S plane. You'll have 2 poles on the right hand side of the S plane. And we know that if we have poles on the right hand side of the S planes, what happened? Right hand side means, if you can tell me what does it mean, the right hand side of the planes. Right hand side means basically sigma represents decay. For the right hand side, the decay is positive. So the decay is positive, it means the signal will keep on growing. Whereas for the left hand side, we have the exponential part, or the decay is negative. It's exponential negative something, here is exponential positive something. That's why if we plot the time response, we can see here the decay keep on growing. So this is exponential x, which is keep on growing. So this is a positive decay, right? So it means as time approach infinity, the natural response approach infinity. So it means that for a bounded input, because we have a specific input, is 1 over s, right? So here is the input. We yields an output which is unbounded. So the output keeps on growing, it is unbounded, so the system is unstable. And from the point of view of S plane, we can see that an unstable system have at least 1 pole in the right half plane. So if only 1 pole situated in this part on right half plane, the system will become unstable, because it will have a component of exponential that will keep on growing. So, and all poles of multiplicity greater than 1 on imaginary axis. So unstable system have at least 1 pole in the right half plane, or poles of multiplicity greater than 1 on imaginary axis. Well, I think this phrase is quite confusing, but if you keep reminding yourself about having poles on right half plane, then it is unstable. That is quite sufficient. So if we summarize a bit, if you have all your poles on the left hand side, you'll have a stable system because you have a decay of negative exponential minus x. But if you have your poles on right half plane, then you have your system unstable because you have a positive decay, exponential keep on growing, right? So that's basically the determining or the deciding parameters on whether a system is stable or not. If only one pole is placed on the left hand side, then your system will become unstable. But if your system has poles that is exactly on j omega axis, it means you will have a system that is marginally stable. It is not stable, it's not unstable. It is what we call marginally stable. It's like a sine wave. Right? So now we look at Routh-Hurwitz criteria. So what does Routh-Hurwitz criteria does? So instead of so I'll read the text first. So it's a method to know how many closed loop system poles. So it's a method to know how many closed loop system poles are in the left half plane, how many are in the right half plane, and how many are on the imaginary axis. So basically it's a criteria that allows us to tell how many of poles is on the left, how many of poles on the axis, j omega axis, and how many poles on the right half plane, right? So by doing this, you can directly know whether your system is stable, unstable, or marginally stable. So there are several steps that you need to follow. It is pretty straightforward. You have to just follow the steps, and according to the results of the execution of these steps, you will be able to tell whether the system is stable or not. Right? So the step is basically, the first one is to generate the Routh-Hurwitz table from your transfer function, and then once you execute the table, once you do all the steps inside the table, you'll be able to interpret the Routh-Hurwitz table. So here we'll see how do we construct our Routh-Hurwitz Routh-Hurwitz table, right? So imagine if you have a transfer function over here. So it is a transfer function, a single transfer function, and you can see that the transfer function is pretty complicated, right? So what happened is basically it will come from a system of quite complex system involving multiple block system. And what we have done actually, in order to get to this, is we have simplified the system so that it can be written as one single equivalent transfer function. So now we have this transfer function. This transfer function is written as, so you can see here, I write ns, which means numerator of the transfer function, divided by a certain polynomial. Why do I write just ns? Because we are not going to be interested in the numerator, because we know who decides. By now we know which part of the transfer function decides the position of the poles. It is basically the denominator. So we will ignore the numerator, we will only study the denominator. And basically Routh-Hurwitz criteria tables treat the denominator of the transfer function in order to come out with basically the conclusion whether the system is stable or unstable. So it studies only the polynomial on the denominator. So here we have an example of a denominator of the transfer function with a power 4. So the order is an order of 4. So we have basically in front of the variable s of the s-plane variable, basically the a's are basically the coefficient. So in front of s to the power 4, we call it a4. In front of s cubed, we call it a3. In front of s squared, it's a2. In front of s is a1. And the final one without s is, we call it as a0, right? So a4 until a0 are the coefficient of the polynomials. So this is the Routh-Hurwitz table that you need to construct before you do any calculation. So Routh-Hurwitz table procedure is divided into two. The first one is constructing or addressing the table, and then there are several calculations that you need to fill in. So the thing that is blank for the moment is the thing that we're going to do in the second step, which is calculation and filling in the table. The thing that we're going to do now in this part is just starting the table. So how do we start the table? The table consists of multiple lines, and the number of lines depend on the order of your polynomials. So here the polynomials is 4, so we will have basically 5 terms: power 4, power 3, power 2, power 1, and power 0. So that's why we have 5 lines. So we start the lines with the highest order, s to the power 4, go decreasing into until the last one, which is s to the power 0. So we have 5 lines: s to the power 4, s cubed, s squared, s to the power 1, and s0. 1, 2, 3, 4, 5. 5 lines. So how do we fill in these lines? We will start with the first 2 lines. The first 2 lines will be filled in with the coefficient of the polynomials. How do we arrange the coefficient inside the table? The first row of the first lines, the first column of the first line, will be filled with the coefficient of s to the power 4. So the coefficient is a4, so we fill it with a4. The second row, the second line, the first row of the second line will be filled in with the coefficient of s power 3, which is a3. So we start with a4 and a3. Here, in the next line, we will fill in with a2, a1, a0, and 0. So in order to remember this, basically it's very simple. You start with a4 and then you skip 1, you put a2, and then you skip another one, you put a0. At the bottom, you put the power of this particular polynomial's order. S to the power 3 is a3, and then you skip 1, so you get a1, and then you skip 1, the next one will be nothing, so it's 0. So these are the thing that you need in order to begin your Routh-Hurwitz table. So in the next slide, we'll see how do we fill in the balance of these 9 squares, 9 columns and rows, 9. So here, basically, just now what we had was, so basically what we had just now previously is just this part. So we have S4, S3, S2, S1, and S0, and we have filled in this part as well. So the denominator ds was basically it's a4 S4 plus a3 S3 plus a2 S2 plus a1 S and plus a0, right? So this was the polynomials. So we had this and this in when we start the tables. So now what we need to do is we have to fill in the other parts of the table. So here basically there are 3 by 3 tables that we need to fill in. So how do we fill in the tables? So let's start with the first one, the first table, the first portion of the tables. How do we fill it in? So in order to fill this, so we do a4, so you take a4, multiply by a1, so multiply by a1, and then minus a3. So the thing in between the modulus, it is basically is like the calculation of a determinant of your matrix. So it's just like the calculation of determinant of matrix. So it's a4 multiplied by a1, right? And then minus a3 multiplied by a2. So we have a3, so minus a1, I repeat, a4 multiplied by a1 minus a3 multiplied by a2. So you got the value inside here. And then you put minus in front of it, and then you divide it by, what they divided by? You will divide by this part of the table. So it's the table on top. So it's the line, the first row of the line on top of where you are filling the table right now. So for example, here we are filling number 1. So the denominator of your calculation will be a3. Okay, so it's a4. I repeat, here in this part of the table, in this case, this square, what you're filling in is basically you do the calculation of a4 multiplied by a1 minus a3 multiplied by a2, minus everything divided by a3. So we'll call this value as b1. We will call this value as b1 for the moment. And then for the next the second square, what do we fill in it? So now here we also take A4. So A4 is here. Multiply by A0. So we skip basically the column that we have on top. So A4 multiplied by A0 is multiplied by this one. And then, no, it's not multiplied by A0, it's multiplied by 0, I'm sorry. A4 multiplied by 0 minus A3. So A3, go back to the first column, to the first row, column, multiply by A0. So you get A4 multiplied by 0 minus A3 multiplied by A0. Again, you put minus in front of the calculation and you divide by, so it's the same thing as in the table that we have beside here. It's divided by A3. So it's divided by the first value of the row on top of it, divided by A3. So now in the third column, so in the third column, what do you fill in? In the third column, it's A4 multiplied by 0. So it's A4 multiplied by 0. What is this 0? This 0 is basically, if we continue the table, we should have had 0 over here, right? So it's A4 multiplied by 0 minus A3. So we go back here, A3 multiplied by also 0. So we got A4 multiplied by 0 minus A3 multiplied by 0, negative in front of everything, divided by also A3. So you see, in each lines, the calculation is always divided by the first value that we have on top of that line. So it's also divided by A3. But here you know that A4 multiplied by 0 minus A3 multiplied by 0, at the end it will become 0. So in this table, the result is 0. If you go to the previous table, the value of this table, the calculation of this will become B2. We call this B2. So we finish filling in the values, the calculation for the line of S2. So we continue in the line of S1. So I call this table is this square as square number 4, 5, and 6. So the calculation are the same. So you see here, it's A3 multiplied by B2. So now, instead of taking A4, you take A3. So you take the value that you have here, A3, multiplied by B2, right? B2 is the value that you have here, minus B1 multiplied by A1. So B1 is this value here, divided by B1. B1 is also the value over here. And it is multiplied by, this B1 is multiplied by A1. So A1 is the value that you have over here. So if we look at the pattern, right? If I take a highlighter now, the calculation for this particular square, basically it involved the matrix of A3, A1, B1, B2. So it involved the matrix A3, A1, B1, B2. So for this particular, to fill in this particular square, what you need is basically 4 square on top of it, right? So now I think I'll not repeat. You can try on your own. So to fill in the square number 5 here, so what you take is A3, B1, 0, and 0. So where is A3? A3 is this one, and B1 is the one that you have on the bottom, at the bottom. So I'll change to pointer and all. So A3, B1, A3 is this one, B1 is the one that's below it, and then the other matrix is basically you skip this part, just like when you try to fill in B2 here. You skip this, so the one is 0 and 0. So now it's A3 multiplied by 0 minus B1 multiplied by 0 divided by B1. So it becomes 0. So the same thing here is A3 multiplied by 0 minus B1 multiplied by 0 divided by B1. So again, it's 0 here. And you do the same thing for the last row. Therefore, you have completed. Once you've done everything, now you have, basically in this example, what we have is a completed Routh-Hurwitz table with all the calculation. So how do we treat the result of this calculation in order to conclude whether it is stable or not? We'll see in the next slide, right? So there's a remark as well, the value in a line. So basically, if you look at a line, for example, take S1, the value, it says that the value in line can be divided for easy calculation. For example, imagine if the value, let's say, we will not take S1. Let's say, imagine we'll take S4 here. A4, A2, and A0. If they are all multiply of 10, you can basically divide every value A4, A2, and A0 by 10 to make the figure smaller and easier for calculations, right? So if inner lines, the value can be divided by a certain number, you can basically reduce the number. So that is not a problem. So we'll see now with the value. So before we conclude that what we're going to do here is to look at an example how to fill in practically the Routh-Hurwitz table. So imagine if we have a transfer function with a unity feedback like this. So the transfer function is written on top on the forward transfer function, 1000 over s plus 2 multiplied by s plus 3 multiplied by s plus 5. And we know that if we want to write and use Routh-Hurwitz criteria, what we need to do is we need to reduce it into an equivalent single transfer function. So if we do the calculation, so by now you know how to reduce it. So you'll get 1000 over s cubed plus 10s squared plus 31s plus 1030, right? So please try to do this. So once you have this transfer function, what you need to do is to fill in the Routh-Hurwitz table. So here we have the denominator of that transfer function, s cubed plus 10s plus 31s, 10s squared plus 31s plus 1030. So the first let me change to a pen first. So we know basically it started with, let me change into a red pen. So it start with power 3 cube and then square. So the highest power is basically cube. So we start the table with s cube. Start the table with s cube, and then it goes decreasingly from s cube to s to the power 0, right? And then the next thing that we need to do is we need to fill in the first two lines. So the first line, the first column of the first row of the first line, what do we fill in here? The thing that we fill in here is basically the coefficient of s cube. So the coefficient of s cube is basically 1. And then here, what is the coefficient that we fill in here? We skip 1, it's not s squared, it's the s. So the coefficient is 31, so we put in here. And then here, what do we put? Is the coefficient of the next one. So the next one is basically 0, so we put 0, right? So it's done for the first line. And then the second line is the s squared. So we fill it in with the coefficient of s squared. It's basically, it was 10. So we start with 10. And then the next one we skip. So we got 1030. So it's 1030. And the next one, if it goes to the next one, here it is 0. So we have 0. Right? So we have filled in the two first lines. So what are they doing in this table? So basically between 10 and 1030, it is just there is a coefficient of 10 that can be reduced. So we divide by 10. For example, here instead of 10 it become 1, and instead of 1030 it become 103. So this will make the calculation much easier. So let's go to the first square where we need to do calculation. So here, what kind of calculation that we do? The calculation that we do here is, so the first value that, so it is a calculation like a determinant of matrix. So the value that we put here, what are they? So here 1 is basically the value that we have here over on top, 1 and 1. 31 and 103 is basically the value that we have here, 31 and 103. So the calculation here is basically 1 multiplied by 103 minus 1 multiplied by 31, everything is negative, divided by, so what do we put here? The value here is basically is the first column of the row on top of this square. So it is this value of 1. And for the whole line, it will always be divided by 1. So here is be divided by 1, here is also divided by 1, here is also divided by 1. So we have completed this calculation. It should be equals to minus 72. So we go to the next square. So square, I'll call this square number 2. So what do we have here? Again, if we look into the slide, the previous 2 slide, so what do we fill in here is basically this 1 comes from these rows, and this 0 come from these rows. So we do the calculation, 1 multiplied by 0 minus 1 multiplied by 0, negative the whole thing, and divided by 1. So this one becomes 0. This one is also becomes 0. So this is the first line. So we have minus 72, 0, and 0. So we have to finish all the lines. So the last line of s to the power 0, what do we put in here? The thing that we put in here is now these 2 rows, lines, and then with these 2 rows. So we have 1 and 1 and minus 72. So 1 minus 72, and here we have 103 and 0. So it comes here 103 and 0. Divided by which value? Is divided by minus 72. So if we do the calculation, we get 103. And here, what do we have here? Here what we have is basically we have 1 and minus 72 that comes from here. And here we have 0, 0 that come from these two square, 0 and 0. And it's divided by minus 72. The same goes for here, you can verify. So at the end you get the value here is 103, here is 0, and here it is also 0. So now we have filled in all the table in this. So how do we conclude when we have addressed, or when we have written the table? When we have fill and complete the table of Routh-Hurwitz criteria, how do we conclude? The interpretation of Routh-Hurwitz table is very simple. Basically, the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So let's see. So the number of sign changes, so how many sign changes have occurred in the first column, will be equals to the number of roots of the polynomial that are in the right half plane. So let's see what does this mean. So we go back to our tables just now, and it says the number of changes of sign in the first column. So we're going to look at only at the first column, right? So we look only at this first column, and it says the number of sign change. So how many times does the sign change? Here we have the sign of this square is positive. Here it is still positive, but now the sign has become negative. So there is 1 sign change. And here again, from this column of S1 to S0, now the sign has become positive. So from this column to this column, we have another 1, and that makes 2 sign changes. So what happened is that we have 2 sign changes. So it says that the number of sign changes will be equals to the number of roots on right half plane. So it means if we plot our S-plane, these 2 sign change means there are 2 roots somewhere in the right half plane. So what does that mean? We know by now that if we have roots on the right half plane, it means it is unstable. So if you have sign changes in the first column, it means your system will become, the system that you're describing is basically, it is an unstable system. So there you have 1 change, and there another change. So two sign changes, therefore two right half plane poles, therefore the system is unstable. So here you have another example, right? So now what we have here is basically it's a polynomial. So you can see here we are not dealing anymore. When we use Routh-Hurwitz criteria, if you have one poles or two poles like in the first order or second order system, it's very easy. But now when you're dealing with a huge system where you can see here the polynomial is basically of an order of 7, therefore it's very hard. It's gonna take a long time to find all the poles. The calculation might be complicated, very complicated. So what we do is we use Routh-Hurwitz stability criteria. So what you need to do is, once you know that the transfer function is given, you draw directly your Routh-Hurwitz table and fill in your Routh-Hurwitz table. And if there are sign changes in Routh-Hurwitz tables, directly you know that the system will be unstable. So for this polynomial of order 7, what you need to fill in is basically, so here the 3 goes into the first column, first row, and then here you skip 1, so you got 6, and then you skip 1, you got 7 over here, and skip 1, you got 2 over here, and then if you skip another one, it's 0, so you don't build the table at point where it is 0. And here 9, you got here s to the power 6, you skip 1 from here, s to the power 4, the coefficient is 4, you put 4, skip 1, it's 8, skip another one, it's 6, so the 6 you put over here. And then the calculation over here, I'll let you revise the slide, the previous 2 examples. So the calculation over here, what is it? It is basically when you take the value from these two columns. So it is 3, 9, 6, 4, right? Negative. So 3 multiplied by 4 minus 9 multiplied by 6 divided by, it will be divided by 9. So this is the value that you should put in here. So let's say we try another one. So what about here? What about here is basically, it's when you take this row and column and this row and column. So it will become 3, 9, 7, 8 minus divided by 9. What about here? Here you will take this and this. So it's 6, 4, 2, 6 negative divided by 9, and so on and so forth. So I'll let you continue to do the exercise. So please try to do this and see and try to conclude whether this particular system is stable or unstable. So now that we have seen basically the method and the steps of calculation in order to construct and conclude the stability of a system using Routh-Hurwitz criteria, we've seen that it is very simple using just calculation that resembles to the calculation of a determinant of a matrix, and by just identifying whether there is sign changes in the system or not. Just by looking at that, we can already identify the stability of the system, right? So the usage of it becomes more evident when we have a certain unknown in our transfer function, right? So because if we have an unknown, for example, here we have a k in our transfer function, identifying the exact position of the poles is not relevant anymore, because if we have, for example, this type of transfer function where we have an unknown k here, what will happen is that the position of poles of your transfer function, even if we see here the transfer function is not the order of the transfer function is just the order of 3, we could say that it might be easy to find the position of the poles, but it is now become not relevant because there are no specific precise position of poles, because the position of poles will change in function of the value of k. For example, if the poles is at a certain point for k equals to 1, if k change value into 2, 3, 4 or other values, the position of the poles also change, right? So I think you get the idea. So using basically if k keep on changing, it means the position of poles can also keeps on changing. Therefore, the risk is that we could have for a certain value of k, we could have the system is stable, but for another value of k, for example, a high value of k, the system can fall into instability, right? So this is basically the kind of problem that can be treated easily using Routh-Hurwitz criteria, because Routh-Hurwitz criteria doesn't care about the exact position of the poles. What it cares about is just if there is sign changes or no sign changes. If there is sign changes, it means that it is unstable. If there are no sign changes, it means all the poles will always be situated on the left hand side and it is stable. So let's see if we have a variable, an unknown inside our transfer function. Let's use our Routh-Hurwitz criteria to identify the stability of the system. So the stability of the system, so imagine now, so we are constructing the tables. So the tables is basically, it goes, the lines we have 4 lines from S3 to S0. So we have S3, S2, S1, S0, and the coefficient of course here is the coefficient of S3, it's 1, and we skip 1, that's 77, so it's 177. And for S2 the coefficient is 18, and then if you skip 1, the coefficient is now K, is 18 and K. And if you do the calculation inside the tables, now the calculation of course in relation to K. So for example, the first calculation here will get 1386 minus K over 18, and here we have K, just K, right? So why don't we fill in this table as well? Well, this table is not important because in Routh-Hurwitz criteria we only look at the first column. If there are sign changes in the first column, then it is unstable. So let's look closely at this one. So we know that there will be a certain range of value of K where it will affect the sign of these two numbers. The first numbers is 1386 minus K divided by 18, and the second numbers is K. So the ranges are, for example, if we look at the value here, the value here, 1386 minus K, if K is smaller than 1386, that means what happens? That means that this value here will become positive, right? If it is positive, it means we have previous two values with positive signs, they are all positive. In order for the system to become stable, here it also need to be positive. So it could only be positive if the range of K is situated at the range of smaller than 1386. So we can say that for any value of K smaller than 1386, the system is stable. And we can also say that if we look at this value here, of course K need to be smaller, but it cannot be negative. It cannot be negative because if it is negative, now if we have positive, but now negative, then it will be unstable. So K need to be positive and need to be smaller than 1386. So there are two conditions: K need to be smaller than 1386, and K need to be larger than 0 as well. If K is larger than 1386, the system will become unstable. So you see, just using Routh-Hurwitz criteria, Routh-Hurwitz table, if we have a variable, we know what value of K should we choose in order. So for example here, where do we have that kind of cases where we have a variable K? It is basically an example where we introduce a controller. So imagine we have a system over here. The system is basically this part. This is the system. 1 over S multiplied by S plus 2 multiplied by S plus 3. There is a feedback with transfer function S, and we have a general feedback loop at the bottom here. So usually what happens is we don't have this part, right? We don't have this part. But in order to improve the system, what we can do is we add another transfer function with a coefficient K. So it is a coefficient with a certain value. What we do is basically, if we add a certain value before the transfer function, we will tend to, it is basically an addition of coefficient in front of transfer function. What happens is that it will speed up the response of your system. If you have K a larger value of k, what will happen is the response will also multiply by k, right? It will be multiplied by k. If it is multiplied by k, then the system will become more responsive and its response quicker. But there are dangers in choosing the value of k. What we're afraid of is basically there might be in this system there might be a certain value. For example, just now we've seen that if k exceed the value of 1386, then the system will become unstable. So this is the case where we use Routh-Hurwitz criteria table. So let's take this example. So in this example, let me take my pen first. So in this example, what do we need to do? What we need to do is basically, in order to use what we want, so by now what it says is determine the value of again k to make the system stable. And we know that in Routh-Hurwitz criteria table, we will not have a specific value of k, but we have a range of k. But in order to have that range of k, we need to write down or construct our Routh-Hurwitz table. In order to construct that Routh-Hurwitz table, we know that Routh-Hurwitz table take a polynomial, one single polynomial, right? So numerator, denominator, and the Routh-Hurwitz criteria take this denominator into the table. So we need therefore to have only one single transfer function with the same input and same output. So now we see that we have 1, 2, and 3 transfer function, 3 blocks also. It's a multiple block system. What we need to do first is to simplify them. So I'll just help you to start with this. So the first thing that we do is basically we can see there is a feedback over here. Let's say I'll call this as GS and I'll call this feedback transfer function as HS. So if we simplify this, you know by now it will become GS over 1 plus GS HS, right? And now that we have simplified this, now it is in series with this what we call this controller K. So it is simply K multiplied by GS over 1 plus GS HS. And then there is another feedback loop that's on the bottom here. So the simplified transfer function will become, so let's say if I call this whole thing now as G1S. So here we have a feedback transfer function of HS equals to 1. So the simplified the reduced transfer function will become now is G1S divided by 1. So 1 plus G1S multiplied by 1, right? So we have in the denominator, so this is the denominator that we're going to put in our Routh-Hurwitz table. So if we look at here, so it is 1 plus, what is G1S? G1S is this whole thing that over here, that we have over here. So it's KGS divided by 1 plus GS HS. So this is this whole thing here is the denominator of the transfer function that we're going to put in our Routh-Hurwitz table. So we can see that in here we have k's, right? So this k will have a certain range where for a certain range of k the system will be stable. So that's the thing that you need to do. So you need to finish this calculation and construct the Routh-Hurwitz table. So I'll let you. So now we have arrived at the end of the video lecture. So I hope by now that after looking at the explanation of what is the Routh-Hurwitz criteria table, how do we build and construct the table, and how do we fill in and complete the table, and then at the end how do we conclude. So basically the conclusion is if you have any sign changes, the number of sign changes represent the number of poles on the right half plane. So if you have even one sign changes, it means your system is unstable. So I hope by now at the end of the lesson you are now able to determine the system stability using Routh-Hurwitz criteria. So this is basically what we call normal cases, the example that we had here, and there are in this slide basically 2 other examples that I hope you can try it out so that you get familiar with the Routh-Hurwitz criteria table to deduce stability, and for sure this will be included in the final exam as well. So thank you. I'll see you in the next lesson.